If you sit inside a modern high-speed train moving at 200 miles per hour, you can place a full cup of coffee on the fold-out table in front of you, and the surface of the dark liquid will remain virtually motionless. You can walk down the aisle and feel completely grounded. Your brain registers the experience as sitting in a quiet, stationary room. But just inches beneath the floorboards, a violent physical reality is unfolding. You are sitting inside several hundred tons of metal, carrying immense kinetic energy, covering nearly 300 feet of Earth every single second. By the strict laws of physics, a mass moving at this speed with this much energy wants to do exactly one thing: travel in a straight line. Mathematically, the moment the track curves, centrifugal force should throw every passenger against the window and tip the carriages into the dirt. While engine power generates this extreme velocity, speed alone does not ensure the train stays on the tracks. The quiet cabin is actually the result of a hidden physical machine, a continuous negotiation between geometry and infrastructure that systematically neutralizes the laws of nature. To understand how a massive vehicle survives a high-speed curve, you have to look at the exact point where the machine meets the Earth. Most people assume a train wheel has a deep inner lip, a flange, that hooks over the track to physically lock the train in place, much like a roller coaster grips a pipe. But at 200 miles per hour, if the flange was the only thing steering the train, the sheer friction of steel grinding against steel would quickly heat up, deform, and shred the metal. It would cause a catastrophic derailment. The flange is a failsafe that barely touches the rail under normal operations. The solution is geometric. The conical wheels slope downward, locked onto a solid axle. In a curve, centrifugal force shifts the train outward. The outer wheel rides on its thicker cone, gaining circumference, naturally steering the axle without a single computer-guided pivot. But solving the curve introduces a highly dangerous problem called hunting oscillation. At extremely high speeds, the heavy wheels constantly seek equilibrium on their cones, causing the solid axle to overcorrect. It shifts too far left, then too far right, oscillating back and forth violently. To prevent this high-speed wobble from shaking the train off the tracks, engineers use heavy physical dampening. Beneath the carriage sits a massive independent mechanical subframe called a bogie. It is packed with heavy lateral dampers that act like giant shock absorbers, arresting the oscillation and bleeding off excess kinetic energy as heat. But steering the train is useless if the earth beneath it cannot handle the load. To keep passengers from feeling violent sideways forces during a tight, high-speed corner, the track infrastructure itself is canted, meaning the outer rail is built higher than the inner rail. As the train hits the curve, this banked track tilts the entire mass inward. It redirects the centrifugal force downward, straight through the floorboards, rather than sideways into the walls. To the passenger, the lateral G-force is neutralized into a slight feeling of heaviness pressing down into their seat. This ground infrastructure faces its own extreme environmental threat: thermal expansion. High-speed rail requires seamless, continuously welded steel ribbons to avoid the severe vibrations of traditional track joints. But in the summer sun, a mile of continuous steel rail wants to physically lengthen by several inches. With nowhere to expand, the pressure builds until the track violently buckles outward in a massive distortion known as a sun kink. To solve this, the infrastructure relies on sheer brute force tension. When the track is laid, it is mechanically stretched by massive hydraulic pullers to simulate the expansion of a hot summer day, and then locked down with heavy-duty steel clips to concrete ties.
The track is held in immense artificial tension, physically fighting the extreme forces of the sun every single day to guarantee a perfectly straight path. Even with perfect track infrastructure, a train moving at 200 miles per hour runs into another physical wall: the atmosphere. At these speeds, air behaves like a thick fluid. The high-speed train is essentially a massive piston pushing through a miles-long cylinder of air. When a train enters a tunnel, it pushes a massive wall of compressed air ahead of it. This micro-pressure wave travels down the tunnel at the speed of sound. If left unchecked, this invisible wall of air explodes outward at the exit in a violent sonic boom, strong enough to shatter nearby windows. Engineers solved this by modeling the train's nose after the beak of a kingfisher bird. This specific, elongated geometry slices the air pressure wave upon entering a tunnel, preventing the shock wave at the exit. Pushing the train through this atmosphere requires a massive, uninterrupted flow of electrical power. The train draws thousands of amps of current using a folding mechanical arm on the roof called a pantograph. This arm must maintain constant, perfect physical contact with an overhead wire barely an inch thick, while moving at 300 feet per second. As the pantograph slides along, it pushes the wire slightly upward, creating a physical ripple that travels down the wire ahead of the train like a wave rolling down a cracked whip. If the train travels faster than the wave it creates, it will violently snag the wire and tear down the entire electrical grid for miles. Infrastructure engineers defeat this wave by pulling the overhead wire to an extreme tension using massive physical counterweights at the end of every wire segment. The tighter the wire, the faster the wave propagates, ensuring the destructive ripple always travels over 300 miles per hour, safely outpacing the train itself. Propelling the train, steering it, and powering it solves only forward momentum. The final, most extreme physical challenge happens when the train needs to safely halt a 400-ton vehicle moving at 200 miles per hour. Dissipating that much kinetic energy using traditional friction brakes, pressing a mechanical pad against a steel wheel, would generate catastrophic thermal overload. The heat would cause the wheel to warp, crack, or fuse completely to the rail. Instead, high-speed trains eliminate physical friction almost entirely. This diagram shows how linear eddy current brakes work. By dropping massive electromagnets close to the steel rail, but never actually touching it, the system induces an invisible, swirling magnetic field inside the rail itself. This creates an invisible, powerful magnetic drag. The kinetic energy of the train is converted directly into thermal energy, safely dispersed within the long stretch of the track, slowing the massive vehicle down rapidly through magnetic resistance alone. By removing mechanical pads and grinding steel during high-speed deceleration, the system prevents extreme structural wear and tear on the wheels, relying on friction only at the very end to bring the train to a complete, final halt. When you sit down, open your laptop, and sip your coffee on a high-speed train, you are entirely shielded from this reality. You don't feel the conical geometry self-centering the axles beneath your feet. You don't feel the heavy dampers bleeding off the hunting oscillation, or the millions of pounds of tension holding the welded steel tracks flat. You don't hear the kingfisher nose slicing the pressure waves of the tunnels, and you don't feel the massive electromagnetic resistance bringing you to a safe stop. When an infrastructural system is designed flawlessly, the violence of moving massive weight at extreme speeds is systematically erased by physical design. It leaves the ordinary passenger with nothing more than a quiet room, a steady cup of coffee, and a blur of scenery outside the window.